Welcome to the introduction video of EasyNodule, the groundbreaking application for pulmonary nodule classification. Developed by the dynamic duo, Kulal and Labshri, as part of their final project at University of Science and Technology Huari Boumediene. But first we will explain our approach to solve the problem of classification of suspected pulmonary nodules. Our research is focused on utilizing artificial intelligence techniques to classify pulmonary nodules, with the goal of improving diagnostic accuracy and efficiency. By employing sophisticated models, we aim to provide automated analysis of pulmonary nodules, enabling early detection of lung pathologies and enhancing patient care. To achieve this, we have developed a groundbreaking approach that starts with pre-segmented 3D CT scans of nodules. From these scans, we extract three meticulously crafted 2D images representing the nodule from different perspectives: X, Y, and Z views. Taking inspiration from the pioneering work of Geoffrey Hinton, our methodology revolves around the implementation of capsule networks. As a result, we have created three specialized models, each tailored to a specific view. In cases where there is disagreement among the three models, we employ three basic methods for final classification: strict classification, majority classification, and threshold-based classification. Furthermore, we have incorporated game theory principles to determine the category of the nodule, benign or malignant. The dataset used to train and test our neural network is the Data Science Bowl 2017, abbreviated as DSB 2017. The dataset consists of approximately 753 segmented nodules of size 64 by 64 by 64. Now let's move on to our capsule network model, which is made up of two parts, an encoder and a decoder. The encoder plays a crucial role in transforming a 32 by 32 pixel image of a nodule into a 64-dimensional instantiation parameter vector that encapsulates essential nodule information. The convolutional layer is responsible for detecting basic features in the input image using 256 kernels of size 9 by 9. The primary capsules, 8 in total, each apply 32 kernels of size 9 by 9 by 256 to detect specific nodule features such as size, texture, and orientation. The nodule caps layer consists of two capsules of size 64. This layer encodes not only the activation of features but also the spatial relationships between these features. The capsules then generate output vectors specific to different nodule classes, such as benign or malignant, by utilizing vector output norms and the squash function. After encoding, the decoding process is necessary to encourage the capsules to select the most relevant features. We apply deconvolution layers to progressively enlarge the vector representation and restore the spatial features of the image. Our goal is to generate a reconstructed image that closely resembles the original image, with the Euclidean distance serving as the loss function. The closer the reconstructed image is to the input image, the better the decoding process. The capsule network model for pulmonary nodule classification has been enhanced through the integration of the Gabor filter. In standard capsule networks, visual features are learned automatically from the input data, limiting the ability to explicitly select features like size and orientation. By incorporating the Gabor filter, originally developed for tasks such as edge detection and texture analysis, the network gains the ability to capture more relevant visual attributes from the nodule images. The Gabor filter operates by convolving the input image with specific kernels designed to extract spatial frequency, orientation, and phase information. This integration allows the capsule network to capture subtle patterns and variations in the nodules, leading to improved classification accuracy and performance. Here is our classification system, which consists of three phases. In phase 1, the system takes a 3D image, 64 by 64 by 64, of a segmented pulmonary nodule from a lung CT scan as input. To optimize the classification process, we select the central slice for each view axis. This reduces complexity and speeds up the training process. In the second step of our system, we apply pre-processing techniques to our 2D images, such as intensity normalization, resizing, and Gaussian filtering to reduce noise. These processed images are then fed into our pre-trained model to generate predictions. The final phase of the system involves making a conclusive decision about the nature of the input nodule based on the three predictions obtained in phase 2. To achieve this, we employ a final classification method. Majority classification. The class that is predicted most frequently by the three models is selected as the system's final decision. Strict classification. If at least one of the models predicts a malignant class, that class is returned as the final decision. Threshold-based classification with coefficients. The predictions of the three models are weighted with coefficients, where the model with the highest accuracy has the highest coefficient. Their average is then compared to a threshold calculated during the training process. Game theory classification. The system creates a zero-sum game where it confronts the views as players, and their strategies are the features calculated from a set of reference images. In our game theory model, we have utilized the following features: energy and homogeneity from the co-occurrence matrix, as well as Hausdorff distance and spectral radius. Here are the results of our models as well as our classification system. Excluding the Gabor filter led to a decrease in loss but a low precision rate. However, incorporating this filter significantly improved the precision rate of the model across all three viewing angles, achieving a minimum of 92%. Furthermore, enhancing the number and size of primary capsule vectors yielded better outcomes with fewer iterations, thereby reducing the duration of training. Based on these findings, we have chosen NodCaps-Net32 as the deep learning model for our application. The majority voting method had the highest precision rate, as all three models had high accuracy for the viewing angles they were trained on. The thresholding model also produced good results due to the calculation of credible thresholds during training. This approach improved the overall performance of the model by using reliable thresholds for calculating prediction averages. Using game theory, we achieved satisfactory results by utilizing features of lung nodules from a set of pre-selected reference images, with a prediction rate of 85%. However, it is important to note that the similarity between nodules can affect the results, as a benign nodule may have similar characteristics to a malignant one. For the strict method, forcing the models to agree did not help with decision-making, as a model trained on one view may interpret the nodule class differently. Now, let's dive into the key features of EasyNodule, a sophisticated desktop application developed in Python specifically designed for clinicians and medical specialists in the field of pulmonary nodule detection.
Upon launching EasyNodule, the clinician begins by authenticating their account or creating a new personal account if they're new to the system. The first window is the Home section, where the application's purpose and description are provided, ensuring that the clinician understands its capabilities. When a patient arrives, the clinician checks if the patient already exists in the database by entering their name and phone number. If the patient is not found, the clinician can add them to the database by providing necessary information such as name, date of birth, location, gender, allergies, smoking history, medical background, family history of cancer, email address, and phone number. Next, the clinician selects the patient from the table and navigates to the Nodule Classification tab. Here, they can choose the patient's nodule, which can be conveniently brought in on a flash drive. By clicking the Start Classification button, the clinician initiates the classification process. A notification sound alerts them when the classification is complete. EasyNodule provides the clinician with multiple classification methods to choose from. Further information about each method can be accessed through the available hyperlink. Moving on to the Report tab, the clinician can generate a comprehensive medical report for the patient. This section contains patient information and the classification results obtained from the model. To examine the nodule closely, the clinician can click on Show Nodule. Additionally, they can consult with colleagues for a collective decision-making process. The clinician then selects the final nodule class and writes their diagnosis. Once the report is complete, they can print it for the patient. EasyNodule also offers a Statistics tab that provides two types of visualizations. The first visualization is a pie chart displaying the number of patients with malignant nodules categorized by location, Wilaya, in Algeria. This visualization helps identify the most affected areas, prompting further investigations into potential causes such as asbestos, radon, or air pollution. The second visualization is a bar chart highlighting factors contributing to the risk of developing malignant nodules, such as allergies, smoking, family history of cancer, and medical background. This chart aids in identifying significant risk factors associated with lung cancer. Looking ahead, we have exciting plans for EasyNodule's future development. Our vision includes implementing a national data sharing network among clinicians to stay updated on patient progress and analyze national lung cancer statistics effectively. Furthermore, we aim to integrate a segmentation model into EasyNodule, enabling a comprehensive application for both nodule detection and classification based on CT scans. With EasyNodule, we strive to empower medical professionals and improve lung cancer diagnostics, ultimately saving more lives through early detection and precise treatment strategies. Thank you for joining us in this presentation of EasyNodule. Together, let's make a positive impact on the fight against lung cancer.